Denicol. So both lectures will be uploaded to our YouTube channel. So if you missed the lecture of yesterday, you can find in a couple of days it in the YouTube. And today, Gabriel will talk to us about initial conditions and kinetic models and other things. So please, Gabriel, go ahead.
Okay, so thank you, Ana Julia. So as she said, this will be a continuation of yesterday's lecture, but on different topics. So if you didn't see it yesterday, in principle, this is related but different material. So yesterday, so this was the motivation for the whole thing. In principle, I did the first two things yesterday. We discussed some general motivation, and we discussed this relativistic hydrodynamic part of the model, the theory itself and how it's applied to heavy ion collisions. Today, in principle and in practice, I will discuss the initial conditions for these models and the issue of particularization and freeze-out, which is a late-stage description of the collision. So in principle, we have these three pieces that we usually clump together to model heavy ion collisions, assuming there was a fluid produced. Yesterday, it was this bit in the middle, the fluid dynamical part. Today, I discussed a little bit about the initial state stuff and the late stages of the collision. That's the plan. But before we go there, I just want to answer some questions from yesterday, briefly, of course, just using some slides and some figures. So someone asked me yesterday about the Knudsen number in heavy ion collisions. So this is just an illustration of that. So this here, on this plot, I show an estimate of the Knudsen number calculated from these fluid dynamical models. And it's calculated in this way here. We just plot throughout the whole evolution of a heavy ion collision the relaxation time, which is proportional to the mean free path. So it's like a microscopic scale. And we compare that to the expansion rate, which defines an inverse macroscopic scale. And we expect this guy to be small if you are in the hydro limit, and if it's too large, we are going beyond the hydro limit. Here is just how this goes in a simulation. This is a spherical collision where we just plot everything in terms of the radius and the time. And there's a color code where essentially blue is good. Blue means the Knudsen number is below 1. So that's in principle the ideal scenario for hydrodynamics. And red is bad in the sense of the applicability of the model. It means the Knudsen number is very large. And this is kind of what we expect of a heavy ion collision. At the very beginning, we start out of equilibrium, and it takes some time for the gradients to kind of decrease. And then we enter some regime where hydrodynamics is kind of applicable. And of course, later, we leave it again because we know that at the very late stages, we're going to just have particles free streaming to the detector, so there's no hydrodynamics there. So we have kind of these two transitions here from something very tough to hydro, something hydro-like, and then later, again, we leave the hydro regime. So that's what we usually expect. This depends a lot also on what is your transport coefficient. So this specific plot is for a specific choice of shear viscosity. But if you change that choice, this would change quantitatively, but not qualitatively. You always have these two scenarios of large, small, and large again Knudsen number. So this was just to answer a question from yesterday with a plot or calculation. The other issue I want to address a little bit more has to do with the interpretation of the viscosities. So we discussed about shear viscosity and bulk viscosity, but you can ask yourself, what do these things mean with respect to the fluid? So in other words, if we extract the shear viscosity and the bulk viscosity of the quark gluon plasma, what does that tell us about the quark gluon plasma, right? So for the shear viscosity, we usually use this kind of pocket formula. This expression here is valid for an ultra-relativistic gas. So it's approximate, but it has all the right physics. So the shear viscosity usually is proportional to the density of particles, the average momentum, and the mean free path. The dependence on the density is very trivial. It's just something that goes with the degrees of freedom. That's why we usually normalize eta by the entropy, just to cancel this out. So we don't really care if the viscosity is large because we have a lot of degrees of freedom. But the main dependence is with the mean free path, or the average time between collisions. So essentially what we have here is that if eta over S is small, it means that we have a lot of collisions, a lot of interaction. So we think of a strong interacting gas. And eta over S is very large. It means the mean-free path is large. We have very few collisions that your system is weakly interacting. So the magnitude of this guy, normalized by the entropy density, gives you that information, how interacting the system is. Now, the bulk is a little bit different. So what about bulk viscosity? Now, in order to illustrate this, I first want to show you the ratio of bulk to shear viscosity for several gases in nature. Non-relativistic gases, so methane, ethylene, a bunch of things, hydrogen, a bunch of gases that you probably heard of, some of them you haven't. And this is the bulk over shear. Naively, you might expect that the bulk is always much smaller than the shear for a gas. But you can see here that this is not the case for pretty much all of them. Like for all of these gases here, or almost all of them, the bulk viscosity is much, much larger than the shear viscosity. And there's a very well understood reason for that, is that the bulk viscosity is large when molecules have an internal degree of freedom, so that when you have this gas, a bunch of molecules are colliding. If these molecules have, let's say, they are polyatomic, they have several atoms, they can start to vibrate. And then you lose kinetic energy to internal energy because everything starts to vibrate. And this is what really leads to a bulk viscous pressure. So in other words, in this case, the bulk viscosity is proportional or dictated by the vibrational relaxation time of a molecule. How long does it stop to vibrate once it kicks in, right? While the shear was proportional to the mean-free path, which is something related to interaction. So for QCD, we expect that something similar happening in the sense of excited state. So when a molecule collides and starts vibrating, it enters some excited state, and then you lose kinetic energy to some internal degree of freedom of that molecule. So in QCD, we have many also excited states in a hadron gas, like resonances, which are produced over some region. And you can expect that the magnitude of bulk viscosity is related to the lifetime of these excited states. So you produce a bunch of resonances and hadrons for some time. You lose kinetic energy to produce these excited states, to produce this mass, and then later they decay back into hadrons. So in this sense, just to close this initial discussion, these are like the two things that have been so far extracted from data when it comes to eta over S and zeta over S, shear and bulk, right? So the eta over S is small, which for us indicates that this is a strong interacting system. So because the viscosity is very small. And the bulk the bulk viscosity has a peak around 250 GV. Sorry, this is 250 MeV or 0.2 GV. So around here, it appears to be larger or the same size of shear. And this indicates that we have some kind of long-lived excited states around this region. So all your systems start to make a lot of resonances and excited states around this thing here. This is interesting because essentially around the crossover region, we don't really know what are the effective degrees of freedom of QCD. It's very unclear. You can think from a hadron resonance gas side, that's a bunch of excited states, sure. But in principle, we don't really know exactly what sits here. So this is just to give you a picture of what we are learning when we measure this stuff, right? And indeed, we are learning something, let's say, more or less concrete about QCD or about what to expect from QCD. Okay, given that, let me do what I actually promised. So now, let's discuss a little bit what happens before we produce a fluid in this collision. At least that's what we assume so far, that at some point you produce the fluid, but you have to discuss how that happens. The real question is we don't really know, but I'll just show you how we model this. So certainly we know something, right? And again, what we have to model here is this kind of initial state description and then how it evolved towards the fluid. So I call this thermalization, but we know that thermalization might not be the right word for it. The more pragmatic term is just something happens where fluid dynamics becomes applicable somehow. Okay, so what is this initial condition we talk about? So in the case of this Israel-Stewart theories that we discussed yesterday, the initial condition is actually a more complicated thing than what you have in Navier-Stokes theory. So in Navier-Stokes, all that you'd need would be the energy density, the net charge density, and the velocity to describe your initial condition of your fluid. Here we need that plus these dissipative tensors as well, because they are now dynamical variables. So you must provide an initial value for them. And that's, of course, an additional complication with respect to this goal of obtaining some initial condition. So we need to know all of these things. In principle, here there is kind of 5 degrees of freedom, 2 for the densities and 3 for the velocity. And here we have an overall of 9 degrees of freedom, which are all of these dissipative currents. Of course, we have to give these fields their spatial dependence at some time, at some initial time where we start hydro. And this initial time is also an ingredient of the model. In principle, we don't really know exactly when we should start hydro, but we kind of know from comparison to data, it's around 1 Fermi over C, roughly. Now, the basic ingredients of most models for this initial condition is to have some kind of criteria for an initial energy momentum deposition due to initial nuclear-nuclear collision. So as you collide heavy ions, what will happen initially is that you have a bunch of collisions between the protons and neutrons inside each ion, and then you're just going to deposit some energy due to that, right? So some initial hard scattering. And then later, we're going to have to figure out how to evolve this initial state, assuming something. Usually, nowadays, the most popular thing is to assume a transport description. So you will provide some microscopic evolution of this initial energy and momentum deposition with transport. This is, of course, an assumption, but so far it's the best assumption, is the best thing that one can do here. So here I'm just going to do what is very common at very high heavy ion collision, just to ignore all net charge and net charge diffusion from the problem. We're just going to assume that everything is 0, which is a good approximation at high energies, and is not a very good approximation at lower collision energies. So of course, this is a limiting scenario here, but it's really, at large LHC energies, it's what you usually do. I'll start with this Monte Carlo Glauber model, which is kind of the cornerstones of all of these initial condition models, the starting point to understand them. And even though this slide, this feature here is actually something that will be applicable to any initial condition model that you ever will do. So the first thing that you do is that before the collision, you sample the position of each nucleon that composes your nucleus using something like a Wood-Saxon distribution. So it's not exactly a Wood-Saxon because here we have some kind of term which is a deviation from spherical shape. So if this W is not 0, it means you don't have a spherical nucleus like lead and gold. Those are spherical, so lead and gold, this W is 0. But some nucleus are not spherical, and then you have a finite value for this parameter. And down here you have this capital R, which is the radius of the nucleus, and this A is the skin depth. Yeah. A good question. Yeah, I could have labeled this wrong. You're right, but it just depends on R, so it has to be spherical. You're right. But it's a deviation from Wood-Saxon. Oh, no, so Gaston asked very well that this term doesn't seem to break any spherical symmetry. So I think I copied this term from some book, but it doesn't seem to be the case. So I think this is more deviation from a Wood-Saxon distribution than a spherical shape per se. But of course, there are nucleus that are not spherical, like Uranus, and you will have to do something, but maybe not this here. For most nucleus that we do, like lead, and gold, this guy is 0, so it doesn't matter. But this here, and also we assume that usually this Wood-Saxon is the distribution of charge inside the nucleus, so just the protons, but we usually just apply it to protons and neutrons. We just assume that protons and neutrons are equally distributed within the nucleus, and that's an assumption. Not perfect one, but reasonable enough for what we do. But here, there's a lot of physics in this. So I don't know if there's a good justification for this procedure, but the idea is that the collision is so violent between these two heavy ions that essentially you are measuring the wave function of the nucleus, and then you localize each proton and neutron just before the collision. So that's kind of what we do here. And I don't know a rigorous justification for that, but this is an essential ingredient for initial condition models. So essentially, we sample the position of each proton and neutron, and then we have a nucleus. We take 2 of these nucleus and we just put them in collision route with some impact parameter, And then we decide if they interact or not according to the inelastic nucleon-nucleon cross-section, which is measured. So whenever the distance between two nucleons of each target is smaller than this, so like a geometric interpretation of cross-section, you just say they will interact and produce particles or entropy.
So if you have,
Yes.
if you have an electromagnetic field, it would affect this distribution. This is a question for all of you.
Maybe.
I mean,
don't know.
if you do have an electromagnetic field after the collision, means that you have one before.
Before, right?
Yeah.
So you're saying, how is the ground state of the nucleus or the wave function of the nucleus affected by an electromagnetic field?
Yes.
Yeah, this could, yeah, I think so, yeah. If it's strong enough. But I don't know if anyone has thought of this in this way. This is before the collision, or immediately before. No, just before. There's a big current of. No, I think
I mean, the magnetic field that is generated by spectators, it will be there, and then you can argue that it will appear just field Fermi before. We don't know how, but I mean, it should be there, right?
Yeah, one should check this, I guess. But I mean, ideally, let's say right now, the thing is, what we really wanted to do would be to sample the wave function of the nucleus. What we do in practice is to assume that we can just sample the kind of one particle wave function of like a Wood-Saxon and just construct the full wave function from combinations of these kind of one particle wave functions. Okay, so if you do that, you'll get something like this. So these are just two nuclei going against each other with some impact parameter B, and each little sphere here or little circle here is just a proton and a neutron that you sample from this Wood-Saxon distribution. And then you check around here, like which of these protons and neutrons will collide, for example. If you look just from the transverse plane, that's kind of the image that you get. So this is the X and Y axis. So the beams, of course, are coming in and out of the slide. In red, we have one nucleus. In blue, we have another sampled nucleus. We see that these circles are kind of the average radius of your Wood-Saxon distribution. So you can see the nucleus the protons and neutrons can pretty much scatter around this distribution. They fluctuate. And in here, we have this kind of theoretical nomenclature where the nucleons that don't interact, we call them spectators. So they don't hit any other nucleon from the other target. So those are in the light color in this picture. And the participants, which are here in dark color, are the ones that, following the previous criteria, they will interact with another nucleon from the other target. So here we have a bunch of these kind of dark little circles, which are all the protons and neutrons that in principle interacted according to this cross-section criteria that we just discussed. The main assumption of this model, and pretty much every other model, is that the energy is deposited where these interactions occur. So you expect somehow that whenever one proton and one neutron from each target interacted, you will deposit somehow some energy. And then the details are how you do that, what is your criteria, and so on. Now this here leads to some fluctuations. So of course, if we didn't have any of these kind of fluctuations due to sampling the position of each nucleon inside the nucleus, the interaction zone would just be this perfect ellipse or rugby ball that you see here. But because we have these fluctuations, the actual interaction zone would be something more like this. So here I tried myself, so there are some errors here, to contour around all these participant nuclei, and we have this kind of fluctuating shape, which will fluctuate event by event, right? Even if you don't change the impact parameter, every single collision will have a different shape that will fluctuate around that elliptical shape that we expect. And this is an event-by-event fluctuation, which has quantum origins, right? It has to do with the fact that we are sampling the wave function of the nucleus and then colliding them. So you have something like this here. So again, we expect all our energy to be somehow deposited around in this kind of fluctuating area here. So how do we do that? Of course, that's when things start to become non-trivial, because you either need a model or a microscopic calculation. So the most simple thing you can do would be just a phenomenological description. So as I said, you just assume that your energy density in this transverse plane, here it could be the energy or the entropy density. That's a matter of choice. Both would be equally justifiable. So for the most traditional thing one can do is just say that your energy density would just be a sum of sources, Gaussian sources, around either binary collisions or participants. These are usually the two types of Glauber models that people would do back in the day. So for example, you can just say that every participant, so every nucleon that interacted, or as people call it, every wounded nucleon, will have some energy deposited there. And then you just sum over the position of all the participants and just add some energy distribution in the form of a Gaussian shape. Then you have two parameters. This kappa would be the amount of energy that you deposited. That's, in principle, a free parameter of this model. You will adjust it later to have the right final state multiplicity. And you have another parameter, which is the sigma square, which is the area where the energy is deposited, the size of the Gaussian, right? And you can do the same thing with the number of, in the position where binary collisions occur. In this case, you have more sources because each nucleon can, in principle, collide with more than one nucleon. So you have way more binary collisions than participants. So if you do this with binary collisions, you have more sources, you have less fluctuations. So these are two versions of a Glauber model. And the answer looks like something like this here. So if you do this procedure with some value of sigma and some value of k, you get some lumpy distribution of energy like this one here in the transverse plane. This is one example of an initial condition from this model. And I think pretty much every initial condition model will give you something like this. You can maybe make it more lumpy by decreasing this sigma, saying that the energy is deposited in a smaller area, so this makes it fluctuate more from point to point. Or you can make it smoother by increasing the value of sigma, by making the energy deposit in a wider area. But either way, it's something like this. So this will give you, let's say, some prediction for the initial energy density that you deposited, right? But you can ask, what about the rest? You also need to know the initial velocity, for example. Is this thing moving or not? Now here, this is a kind of zero-time approach. So we are thinking that all of this happened almost at the very beginning of the collision. So you can argue that the initial transverse velocity is very small. There's no time to develop any transverse velocity. There will be some longitudinal velocity for sure, but that's another story. And also you have to think about what about these dissipative currents, the bulk viscous pressure, the pi mu nu, the shear stress tensor. What about these guys? So usually in this kind of description, you know nothing about them. Quite often you just set them to zero, ignore their existence, or you have to find some other way to describe them. And that's a big problem. So usually that's the hard part. Finding the initial energy deposition, you can kind of find with general arguments, just thinking about, we put some energy here and there, we sum it all together, but finding the velocity is just more complicated. There is another version of this model, which is called Trento model. It's essentially a generalization of what I just showed you before. And this Trento model is the most used model for initial condition nowadays, right? In pretty much all of the Bayesian analysis performed by the Jetscape collaboration, it's using this Trento model. And it goes like this. They do it with the entropy, so they just calculate the transverse entropy distribution with this formula here, where Ta and Tb are the nuclear thickness functions of the proton on each side. So it looks different, but it's very similar to what we had before. So this guy here is just the integral in the longitudinal direction of the density of the proton around each participant proton. Here I say proton, but it could be a neutron as well. And you sum that for each proton or neutron that participated in the collision, that interacted. This W is again another parameter. And they assume that the integral of the distribution of the proton density is like a Gaussian. So in the end, you just have a bunch of sum of Gaussian sources for each nucleus. You have nucleus A and nucleus B, and you combine them in this way, just for the following reason. So if you then vary P, you can actually probe several different scenarios just by changing one parameter. So if P is 1, this is Ta plus Tb. And if you look carefully, it's exactly the same as this here for participants. So you recover this kind of scenario here of just adding a bunch of Gaussian sources of energy for each nucleon that participated in the collision. If P is 0, this tends to Ta times Tb is more like considering the binary collision scenario. And you can vary like a bunch of stuff if you go from minus to plus infinity. This is a very convenient way to kind of probe several possibilities of energy density sources. So here again, you have in principle, three parameters. This P, which you kind of continuously exchange between different scenarios. This guy here is a proportionality parameter, so you can kind of readjust later how much entropy you have in your system. This is a free parameter. And again, the size of the proton to some extent, how much or how wide is your parameter for energy deposition. And I guess this Wi is a new source of fluctuations out here, another parameter, where you can just make the deposition of each source a little bit different from participant to participant. So either way, this is very phenomenological, and it's very simple, and that's why it's very used. At the end of the day, I mean, what some people want is a model where you can kind of continuously probe several scenarios, so that then you let the Bayesian analysis decide which one is the best one, instead of a microscopic one. But of course, one thing that you could do is, instead of asking, you know, how is my energy deposited, you can just use Pythia, for example, and do a more microscopic approach. Okay. Sorry? P, you mean for Pythia or? Okay, so how is P selected? So usually it's selected from the data. You check, you fit it, yeah. One number. So what they do in this Bayesian analysis is that, of course, first they have a prior, so they check, they run simulations for several values of P, and then later they figure out which one is the most likely one to fit the data. If I recall, it's this 0 here. It's kind of TA times TB. So that's the one that so far is winning. But this P parameter is why this model is so attractive. It kind of continuously interpolates between several possibilities, and then you just let the data decide. People are happy because this combination looks a lot like a very famous model called IP-Glasma. And IP-Glasma is very similar to this TA times TB scenario, so people are very happy about this result. But yes?
No, but which data you compare to?
Heavy ion data. Like you just fit everything. So in principle, in this Bayesian analysis, you have these three parameters here for these Trenton models. That's one of these parameters. Plus everything else. So things that I showed yesterday, shear and bulk viscosity, initial time, all these parameters are just varied, and then you select the optimal ones to fit the data. And the data usually is the multiplicity, the mean PT, and these VN coefficients. That's usually what you fit. And then you can extract most of these coefficients. Okay? Yeah, all at the same time. Yeah, it has to be. Yeah. Yeah, and they do happen. Yeah, yeah. But some of this information survives through the evolution. So of course, some parameters you can actually obtain the answer that you just cannot extract them. Like there's nothing on the data that is sensitive to them, and that's a result itself. I would argue that some parameters should not be extracted even. It's good when you find that many values can exist, because
yeah, that's what I was gonna ask.
Yeah.
I mean, when you optimize it, you get values for the parameters or sets of values.
You get distributions, so you essentially get like how likely a given value of P, is. So usually the peak of the Gaussian is like the most likely value, and then as you go beyond 1 sigma, 2 sigma, this becomes less likely that these will fit the data. So likely in the sense of describing the data, right? Okay, so what do you do next? So let's say you have this initial energy distribution in the transverse plane, and then you have to figure out how this lump of energy kind of thermalizes, how it becomes a fluid. That's very difficult to do, but I'll tell you right now what is the main model to describe this, and it's transport theory. So they call this a compost model, and it's based on and QCD, effective kinetic theory description, which of course is valid at very high temperatures, very high energies. You can essentially describe QCD in terms of a kinetic theory, like where F is the momentum distribution of quarks and gluons, for example, and it changes due to collisions, binary collisions or Bremsstrahlung, and so on. So this is like a very, in some sense, simple equation compared to QCD, so it's something you can solve. And then they just assume that essentially all of this lump of energy that we produce at the very early stages is just a bunch of partons. You provide some initial momentum distribution for these partons. So of course, if you want to solve this equation, it's not enough to know how much energy you have in each space-time point. You need to know a lot more. You have to know at each space-time point what is the momentum distribution of the partons there. And in this model, they use something like this here, which usually is kind of a solution from kinetic theory in the oversaturated limit. When you have a lot of gluons, some people argue, Jürgen Bergers and Soren Schlichting, that the distribution of momentum looks something like this here, with this additional parameter psi, which is the momentum anisotropy. So this tells you how much asymmetry you have between the longitudinal direction and the transverse direction. But this here is just one ansatz, essentially, right? So I don't think there's a right answer for this here, but this is just a reasonable choice to start this thing. So again, you need more information than just the energy. You need to know this kind of microscopic information, the momentum distribution of the partons. You evolve this with this, following this equation of motion here. And then after some time, or after any time, you can calculate your T mu just by integrating this F over K mu and K nu. So given some distribution of momentum of quarks and gluons, we know the T mu. And then you can get some initial condition for hydrodynamics, the initial value of T mu. And the whole point is, how long do you have to run this to have a reasonable T mu for hydrodynamics? That's the real question, right? And usually it's 1 Fermi over C, but there's a caveat, okay?
What exactly is the role of gluons in this?
I think this here is essentially for gluons.
But you said that you assume this F0 if you have saturation of gluons. How do you determine?
Assume this is zero, sorry, zero?
No, this F.
Yes.
This F function, F0 function.
Yeah, it's F0, yeah.
You can use this if you have a lot of gluons.
If it's oversaturated, a lot of gluons, yeah. So this is in the saturation limit, or they call it over-occupied limit, where you have really, at very small momentum, a bunch of gluons, and then they argue that the distribution function is self-similar, it has certain properties from the Boltzmann equation, and this gives you kind of this ansatz. Again, so this is not set in stone, right? It's not set in stone. In principle, it's not like this is the answer. It's just a reasonable choice. If you want to solve this problem, it's a reasonable choice.
Mm. So you take some limit to get there.
And the limit is very early times, and they assume also a lot over-occupied limit. There's a lot of gluons, for example.
Okay, so we were talking yesterday, so in principle, this momentum anisotropy wouldn't be affected by electromagnetic fields because it's gluons, but if gluons are interacting with fermions, then this could be a parameter that could be...
So when we talked in the car, right? So not during the seminar, for those who don't know, we talked afterwards. So yeah, that's true. So this system, of course, in principle, there are quarks here, but people expect to be dominated by gluons. Gluons have no electric charge, strictly speaking. So, but they can still be affected by electromagnetic fields due to some kind of dipole term. The gluon can split into a quark, antiquark, and go back to a gluon. But this is an important point. I mean, so all of this here, in principle, is at the very early stages. This is at very early stages. So during this time here, the electromagnetic fields are very large, extremely large. And to be honest, this is not taken into account in any of these models, right? So for any of the things I'm talking about, it's as if these fields don't even exist. But in principle, they're here. And one can check if they will make a difference. Okay, so you solve this. Let me just tell you some features, right? So of course, this is for massless quarks and gluons. So it's a conformal system. Trace of T mu is 0. But we know QCD is not conformal. So that's already a difference between this kind of kinetic description and what we will have at the beginning of a heavy ion collision. In most applications, this effective kinetic description is not implemented with a small coupling, and that's the big deal here. So in principle, this approach here is valid at very large energies when the coupling is very small, and you can have a kinetic theory description. But what is usually done for our purposes is that we just take this and we kind of apply it beyond this domain of applicability. We just assume that this will remain valid even if I crank up the coupling. QCD. Oh, here? Where does it appear here? It will only appear inside these collision terms. It's hidden in the collisions, right? So this coupling will tell us how often these quarks will collide and these gluons will collide. And in order to get thermalization, they need to collide a lot. If they don't collide at all, this will never thermalize, right? So usually when people apply this, they kind of crank up the coupling a little bit. And then, of course, the system will kind of thermalize, or not thermalize, but will approach something that is reasonable to be used for hydrodynamics. So for instance, if we do nothing and use some like crazier model, what happens is that if we take the T mu and put in hydro, the code doesn't even run. So when I say reasonable for hydrodynamics, means we put in hydro and it runs. At least it runs, and we can get a solution and so on. So this here does not really thermalize. So in other words, what is thermalized here? So here thermalization is very well defined. Thermalized means that this distribution function approaches either Fermi-Dirac or Bose-Einstein distribution. So that is what it is to thermalize. And here this doesn't really happen. But it at least something that matches well Isler-Stewart theory. So if we stop this thing and we start Isler-Stewart, there's not a big discontinuity in the model, in the simulation. So this already makes us happy enough to use this and so on. But of course, it has several limitations. Now, in practice, when people do Bayesian analysis, in particular the Jetscape collaboration, they even use something way simpler. They use a free streaming model. So they just go there and say, okay, fine, let's say this is 0 anyway, and just run the Boltzmann equation without any collisions. So the partons just free stream. And this may look very silly and unreasonable, but it's actually really used. I mean, and in the most famous analysis, because this is just much faster than running this kinetic theory, and it actually does pretty much the same job somehow. And so this is actually used in state-of-the-art Bayesian analysis. And when you free stream, actually you have one advantage. I mean, you can make the free streaming velocity a free parameter. You don't have to have just massless partons moving with the velocity of light, but you can just have any velocity you want. So this is a very widely used model. Okay? So this kind of concludes what I wanted to say about these general features of initial condition models. Essentially, two features, as I said, some energy deposition, and then later you need to have some kind of microscopic evolution of some F, if you assume a transport case, to really know the initial T mu for hydrodynamics. So with this approach here, you pretty much get the full T mu, and it's not that unreasonable. Now let me just tell you a little bit about the coordinates that we use in heavy ion collisions. So in heavy ion collisions, we usually don't solve these simulations, either transport or hydrodynamics, in Cartesian coordinates. We actually use these kind of co-moving coordinates or hyperbolic coordinates where we have some proper time variable, which is t squared minus z squared, and these are the Cartesian coordinates, and some space-time rapidity, which is given by the log of t plus z over t minus z. So this space-time rapidity is additive under longitudinal boosts, or Lorentz boosts in the longitudinal direction. And you have this advantage that, so at the very early stage of a heavy ion collision, you have a very strong longitudinal expansion, because that's where most of the momentum is initially, right? You have these two nuclei just moving towards each other in the longitudinal direction, and essentially they just pass through each other initially, and you have this very strong longitudinal expansion. And this coordinate kind of captures that a little bit. So if you go to this coordinate system, it's kind of co-moving with the fluid in the longitudinal direction. And it looks like this if you compare with the Cartesian coordinates. So this is t, time, and z. And this hyperbole here in purple and blue are the constant time hypersurfaces. So we start our fluid in these kind of hypersurfaces, which are purple here or blue here. That's when we set our initial condition. We don't set them in like constant time. That wouldn't make much sense. And the main reason for this is that thermalization is a local process. So the thermalization will happen locally, which means that, and since it's local, different fluid elements will thermalize at different times. So there's no reason to believe that everything will be thermal at some constant time. It's just more reasonable to say it's thermal at some constant proper time. And this eta here is just kind of an angle variable in this plane. So eta equals 0 just shoots up. Negative eta shoots in this direction, and positive eta in this direction. In heavy ion collisions, it's very common to assume that the system is approximately Boost invariant, which just means that everything is just constant in eta, at least up to a given range. And that's why I was just talking about the transverse initial profile and just ignoring everything in the eta direction. If you don't want to ignore it, you do some parameterization like this. So you can say the entry production kind of factorizes. It's some transverse distribution, which is what we calculated in the previous slides, times some kind of longitudinal profile, some envelope, which is just something flat, and eta flat is just how flat it is in rapidity, and then decays very quickly to 0. And with this, you can pretty much describe the number of particles per rapidity that you measure. So you see that in the center is approximately flat. This is a reflection of the fact that the entry profile is also initially flat in rapidity. Oops. And the approximation that we often make is that it's just flat everywhere. So this whole thing is just constant, theoretically. So this h is just set to 1. We just ignore it. And the limitation of that is that then we just describe our system around 0. So let's say we don't care about our simulation describing this whole profile over eta. We just want to describe it around 0. Then you don't have to do a three-dimensional hydro evolution. You can just do a transverse hydrodynamical expansion in these kind of coordinates, and everything is fine. You don't waste your time running, let's say, three-dimensional hydrodynamics. And this is widely employed. This is so popular that it's even employed when it's wrong. So for example, in proton-lead collisions, you cannot do this because it's an asymmetric collision. There's no Boost invariance. But people still use 2 plus 1 dihydro to make estimates for these collisions. So this is like a very popular simplification, even then when it's not that well justified. So with that, I want to move to the next sector. So here, of course, I didn't give you a very detailed explanation of initial condition, but just a general flavor. Now let me talk about what happens at the late stages here, which is the so-called particlization and transport description of the late stages. Again, the goal is to give a general idea and not to go through many details. Now, the most important thing is to not confuse this thing here with hadronization. It's very common that people think freeze out equals hadronization, and that's why people came up with this very funny name called particlization, which I don't think exists. It's just a name they gave to this process, which is the process of making particles or exchanging fluids to particles. Let's just imagine this here is not the QGP, but a gas of hadrons. So again, we already had our hydrodynamical evolution. We had the QGP. It cooled down, and now it's a hadron gas. So this is like a hadron gas. And then I come here, I take this fluid element, and I count how many hadrons are here. Right? How many pions, kaons, and protons, and so on are inside this fluid element. I also not only count their numbers, but what is their momentum distribution. And I just exchange this fluid to hadrons. So I just exchange from that to this. So now instead of having the same fluid as before, described in terms of hydrodynamic fields, I have just a collection of hadrons. But it's the same system. I didn't change anything. I didn't hadronize anything. I just converted fluids to particles. That's all that I did. And why do we do this? It's just because at the end of the day, what we want to do in heavy ion collisions is to describe what you measure. And what you measure are free-streaming hadrons. So hydrodynamics can never describe that. You can never go to the free-streaming limit with hydro. So at some point, you need to switch description to transport, where you can actually go all the way to free-streaming limit, and then compare to observables. So from here on, we pretty much take all these hadrons here, and we describe their evolution with collisions and decays, all the way until they don't interact anymore. And that's when the simulation is finished. So this is what's called particleization, right? Okay. Now, we are not the only ones who have this problem, so I just want to give an example to the aerodynamics of space shuttle, just to make sure you understand this has nothing to do with hydronization, because there's no hydronization here, right? So when you, for example, want to investigate aerodynamics of space shuttle, it's a very difficult problem, because as in heavy ion collisions, you have to describe a system that starts very dense, like the QGP, and ends extremely dilute, like free streaming hadrons. So how do you do that? In this case here, the space shuttle leaves, of course, the surface of our planet, where the atmosphere is very dense. And then it goes through all the way to space, where the atmosphere is very dilute. So you have to describe the interaction of this space shuttle with a gas that is changing the density by orders of magnitude. So in here, the Knudsen number goes from something very small, and at the very end, something very large. So in this case here as well, you must start with some fluid description. So initially, your space shuttle is going against a fluid, and the fluid is a dense atmosphere. And at the very late stages, it's going against a very dilute gas, which cannot be described by a fluid anymore. And from that point on, you describe it with transport. So this is the same problem that we have in heavy ion collisions. And the challenge is, in summary, describing a system where the Knudsen number varies orders of magnitude throughout the evolution. You start very dense, and you end very dilute. And there's no way hydro can describe all of that. It's just impossible. This here is just to show, in terms of results, if these things matter. So here I show you the multiplicity of pions, kaons, and protons as a function of, yes?
In your description of particleization,
Yeah.
it happens in a smooth way, or it's like from a certain instant of time, it becomes...
So I'll come to that. So
Okay.
it will be, so in the illustration I just showed you, it's a constant time, but in practice, it will be a constant temperature. That will be my next slide. That's a difficulty, because at constant time, we don't have simultaneously dilute system. Like at any time, we may have something very dense in the middle, something very dilute at the edge, and you cannot just particleize that. So we usually do it at a constant temperature. But this will be my next slide. So here, just, yeah.
In a simulation, like at a certain temperature, it
Maybe,
is
yeah.
a fluid, and then suddenly...
No, it's always a fluid. So that's the tricky thing. So you can only switch when both descriptions are compatible. So I can only switch from a fluid description to a transport description when both apply. So they're essentially equivalent descriptions, so then I can switch. And then as I switch to transport, then later, of course, hydro will no longer be applicable, but I have already switched. If you switch when they are not compatible, you're just making a mistake, because you are switching between
Okay,
descriptions.
go ahead, then.
And people do this a lot. This mistake is done a lot. But let me just come to this, which is what you asked. So what we do is actually this here. We don't switch from particles, from fluids to particles at some time. We switch, for example, at some constant temperature, because temperature is a good parameter to say how dilute your system is. So the idea is, when the temperature is small, my system is very dilute, and it's already in the hadronic stage. So at some temperature, hypersurface, so some hypersurface with constant temperature, I start counting particles, as I said before, and this is done using the so-called Cooper-Frye formalism. So here I say that the spectra of measured of particles that I put in my transport cascade is given by some integral over some hypersurface over the momentum distribution of particles. So here I'm just counting particles per unit of momentum in over some given hypersurface of constant temperature, for example. It looks kind of like this here. So this is a projection of a simulation. So like in the x direction, and this is the time. And here we have, let's say, constant temperature hypersurfaces of this hydrodynamical simulation. So here, for example, is 150 MeV, this red line. This is usually where people freeze out, or not freeze out, sorry, when they particleize. But here I also show you several other constant temperature hypersurfaces. So what we do essentially is, okay, we take this temperature here. We say, I'm already in the hadronic phase. So at 150 MeV, I already don't have any QGP anymore. It's a hadron gas. And here, and also this is still we think in the hydro limit. So in principle, hydro is applicable, and we can also have transport applicable. We can switch. So we start producing particles all the way in this red hypersurface, And that's our initial condition for transport. We just feed that into some transport description, which will then make collisions and decays for these hadrons. And that's very complicated to do in practice, but the idea is simple, right? Produce particles here, and by produce I mean exchange fluid to particles. The particles are always there, so don't be misled by the word produce. It is produced in the sense of just counting. And then you just evolve the decays and scatterings.
And the freeze out would be another curve.
Yeah, freeze out would be after here. So as these things will collide.
But it would be something like that.
Would be some surface, but it won't be a constant temperature. It will be just some surface where there are no more collisions anymore. And that's what freeze out is. It will be some way beyond here. Okay, so this is kind of what is done. Now there is a problem. I should tell you that when we count particles, let's say I come to this little fluid element here and I say, okay, how many pions I have here? I don't know how many of you have done that in practice, but the answer is usually not the one that you expect. So when you come here and say, how many pions do I have here? The answer is usually like 0.2. So you don't even have a pion, right? So this is the problem, that this system is not very dense. So if you take a very small fluid element, usually you don't have that many hadrons inside. So we do have a problem of statistics here. But if you integrate over this hypersurface, you actually get something more sensible. So this fluid is not as dense as we might expect. But coming back to this formula here, if you're just running transport, if you don't care about anything else, yeah. What do you mean if you, the transport? Simulation or hypersurface or? Yeah. So here you can, the time is right here. So let's say if you run hydro and all that you care is about reaching this hypersurface, you have to run it around 11 Fermi and so on. If you want to run to a smaller freeze-out temperature, you need to run more. So it costs more, right? The later you freeze out, the more it costs you in terms of simulation. When it comes to transport, this kind of, in this specific simulation. So here, I don't think this is a central collision. So the more central, the more dense, the longer also this will take. So it will depend also on how much initial energy you have as well. If it's a very peripheral collision, this could be very quick. You can just run. I think hydro is faster than the transport that comes later. Okay, anyway, so if you run transport, so as I said, in my case, I'm more used to hydro. So for me, I run hydro. All these guys that do initial conditions, they kind of work for me, right? They do it for me, I use it. Now, if you run transport, you think the other way around. Right? All these hydro people, they work for me. They make my initial condition. I'm the most important person in the world, and I'm going to do this, and I will evolve it with transport. That's what my life is. So for them, hydrodynamics is just a way to calculate this hypersurface that you use, and also to know the value of the fields in the hypersurface. So what is the velocity at the moment of freeze-out? What is the pi mu at the moment of freeze-out? But here you have to know something very important. Yeah, in your final state. And for them, that's the only thing that matters. People who run hydro, their output is this freeze-out hypersurface, period, nothing more. You can throw everything else in the garbage. Unless you do jet quenching or photon production, then maybe you don't throw it in the garbage, but if you do soft physics, you can throw it in the garbage. Now the problem is, and this is the fundamental problem in this description, that you have to know the momentum distribution of hadrons inside your fluid elements. You really have to know, if you want to count particles, you have to know the momentum distribution inside the fluid. That's the big unknown here. And in principle, we don't know that. So in hydro, we just know the value of T mu, but we don't have any idea about what is the momentum distribution of hadrons inside that fluid element. So if you want to do this, you need additional modeling. So this is kind of the problem, right? This is what we have from hydro, T mu and the net charge current, which are some integrals of F. And from this information, I need to get F. Of course, this problem is not possible because there are many Fs that could give you the same integral. So this is an undetermined problem. Of course, if I have some F, I can always get T mu. That's the initial state problem I was describing a while ago. There we had this F, and we just calculate T mu. Now we have T mu, and somehow I have to figure out what is this F, right? So in general, this is not possible. But if you are in the fluid dynamical limit, you can do this. to a level of approximation. So here we must assume that hydro applies. If hydro applies, you can estimate this F, at least a small momentum. If hydro does not apply, then there's no hope of doing this, right? You just don't have enough information to reconstruct this momentum distribution from these two fields. This is a very big unknown in the field. It's not the thing that people study the most, but this, for example, is very important if you want to describe what we call differential observables. So the spectra of particles is a function of transverse momentum, V2 is a function of PT. For all that, you need to know this guy very well. And that's why in this Bayesian analysis, they always try to avoid these observables. They always look for integrated observables, like total particle number, average transverse momentum, total V2, because then if we integrate over momentum, we are kind of smearing out this effect and trying to minimize it, okay? So this becomes this kind of problem. So how do we go from the Boltzmann equation to hydrodynamics? Or what is the F, or in other words, what is the value of this momentum distribution function of my gas in the hydro limit? Because going from here to here means calculating this F in the hydro limit. So a very specific choice or framework. So what is the hydro limit? So again, just to quote this, so this is the Boltzmann equation, which is the same equation that I was using before for thermalization. In that case, I was using for a gas of partons. Here, I'm thinking of using it for a gas of hadrons. But it's the same formalism. It just describes, so the main variable is this F, which is the momentum distribution of your particles. Here, hadrons, pions, kaons, and protons. And this equation tells you how this F changes with space and time due to collisions. So this guy here is just a notation for something very complicated, which just tells how this F changes because there are collisions in my gas. The hydro limit is the limit where your distribution function changes very slowly in space and time. So you're trying to find some very specific limit where your system varies smoothly in space and time. So this derivative here goes as 1 over L, and L is very large compared to the mean free path, right? So you're thinking that this guy here is just very, very small. This would be the hydro limit. And so you search for solutions of F, which vary extremely slowly in time, or search for solutions where the derivative of F is extremely small compared to the 1 over the mean free path. This would be the hydrodynamic limit of a gas. So if you have that, you turn everything into a perturbation problem. You essentially think that this equals that, but I put a 1 over epsilon parameter here to remind myself this here is very large, or this here is very, very small. And you find a perturbative solution for your distribution function, just in powers of epsilon. And so in this case, you have a very clear solution. So when you have a separation of scales, you kind of know what solutions of F to expect. And this is what will make it possible to exchange from fluids to hadrons at the late stage of a heavy ion collision. Sorry? Oh, Hilbert Chapman. So sorry, I didn't even say, but this expansion was first envisioned by Hilbert. So Hilbert was the first person to ever do this here in the Boltzmann equation. And this was very remarkable. So Hilbert's derivation, he only calculated this F0, and he showed that this was the equilibrium distribution function, and he obtained ideal hydrodynamics. That was the first time in history someone derived hydrodynamics from a microscopic theory. So it was a historical event. And then later, but Hilbert, in his naive expansion, he couldn't get Navier-Stokes theory. He got something different called Hilbert theory. But then these two guys here, Chapman and Enskog, they showed how this could be done to obtain, as the leading order correction, Navier-Stokes theory. And then they derived for the first time the Navier-Stokes equations from a microscopic theory as well. So I think this Enskog guy was a high school teacher. This was his hobby, and he did this all. And this Chapman guy was a very famous English mathematician. And I think he realized this guy had done something similar to him, and he made sure that he got the credit. So it's very honorable of him. Some people would maybe just kill him, right? Okay. He did the same thing as me, I just kill him. In Sweden, yeah, in Sweden. So yeah, he was like a hobby, right? So if you do this, so again, if you do this, the zeroth order truncation is something like this. So your F, so as I said, the left-hand side is very small. That's what we want. So to leading order, we just find the distribution where it's just 0. And this is very famous. It's the local equilibrium distribution function, just Fermi-Dirac or Bose-Einstein distribution. So the leading term in this expansion is equilibrium term. And the first order truncation is something like this. It's way more complicated. You have that some kind of linear collision operator applied to the first order correction must give you some gradients. So I won't explain with more detail, but this is complicated because you have to invert this operator here to solve this problem. So in heavy ion collision, this would imply that if you want to kind of know this answer beyond the trivial answer, which is an ideal fluid, you would have to know how to invert this operator, which means that we have to know how to model the collisions between all the hadrons that we have, pions, kaons, protons. Almost impossible. And that's when we kind of usually give up and say, okay, let's do something simpler. We do this relaxation approximation where this collision term is just simplified by this here. So you just say, instead of saying that I have collisions and all this complicated stuff that makes my system equilibrate, I just say that essentially all the physics I need is that my system goes to equilibrium over some relaxation time. And if you do this, and here I make some propaganda for myself, so this RTA here is a little bit incorrect. If you want to know how to do it properly, you can read this paper here that we wrote. But they're just advertisement. And in this case, you get some answer like this here. I just want to flash you the answer. So this is an example of things that we use in heavy ion collision. So now this delta F here, we can write in terms of just pi mu nu and bulk viscous pressure. So these are things I know from hydrodynamics. So I can actually just from pi mu nu and from the bulk viscous pressure, reconstruct this momentum distribution. Is this exact? No. It's valid only at, let's say, small momentum. If I go to very large momentum, you can start having some mistakes. But this is just a proof of principle that, in principle, if you are in the hydro limit, you can at least estimate this correction here, and you can perform some phenomenology, okay? So this is a very difficult problem. It's not unsolved. This is a solution in this kind of RTA approximation. But to be honest, people use this in the data. Right? This is one of the delta Fs that are used when they calculate, pions, kaons, and protons, and when they do Bayesian analysis, okay? Just to show you another possibility is just completely orthogonal. So one way, and this will just be a few slides, one other thing you could do is, okay, fine, I don't care about collisions, I don't care about microscopic interactions. Why don't I just guess this F? So let's just guess it. So then you do it the following way. Let's just say we start from this ansatz here. So my F looks something like equilibrium, but this Y here is not the equilibrium value. And then you calculate the deviation from equilibrium, and you expand it as a Taylor series for momentum. So you just say, okay, this is some expansion here. I can go on forever. For small momentum, you can write it as something linear in this delta Y. And then comes the fundamental step, which is this momentum expansion here that you started, you just truncate. I'm just going to stop. I'm going to say, okay, I do heavy ions. I don't care about large momentum. I'm just going to stop here up to the quadratic term. And why would you do that? Why would you stop exactly at the quadratic term? There's actually a reason. If you do that and you count how many coefficients you have, you'll see that epsilon, epsilon mu, and epsilon mu nu, this guy is symmetric and traceless, there are exactly 14 expansion coefficients. And that's exactly the same number of independent components of n mu and t mu nu. So if you want, if you stop here, you can just say, well, I'm just going to choose these guys to have the right n mu and the right t mu nu. The answer will look like something like this, where all of these guys are thermodynamic functions. So I'm not going to write them here. They're huge. But if you just say, this guy goes with bulk, this guy goes with bulk and heat flow, this guy goes with bulk, heat flow, and shear. And these are all things we have from hydro. So in this sense, I can reconstruct this F, right? And the most famous thing you get is that if you only get shear viscosity, you don't have bulk and heat and any diffusion, you get this delta F, which is very famous. And this is pretty much used in almost all of the simulations that you ever see with only shear viscosity. It's just pi mu, p nu, times 1 over epsilon plus pt squared. Looks very simple, right? Could also be completely wrong, but it looks very simple. So that's kind of the other way to do it. You just simplify it as much as you can, and then you just match it to have the right t mu nu, and then you use that. So that's something that one can do. This here is just showing that this could matter. So here I have extractions of eta over s and zeta over s for this 40 moments grad. This is this one here. People do it like this. This other side here is for this Chapman-Enskog RTA, the one I showed before. And there are two other choices down here. It's called Pratt McNellis, so they had their own delta F choice. And this is Pratt Bernard, another. You see Pratt is everywhere, so he's trying a lot. And you see that for each choice, you kind of get different values or different extracted values for these transfer coefficients. So these things could matter at least a little bit in your extraction. So here, just to show how this enters in particle multiplicity and mean PT of pions, kaons, and protons. Here I show this, the calculations with and without delta F. So if you just remove this delta F contribution altogether, that's the difference between the solid lines and the dashed lines. And you see a lot of effect on the mean PT of pions. This may look small, but the fact that this is visible, it's already enough to make you a little bit worried, at least. So this is a huge effect on the mean PT of pions, for example. So you have to worry about this at least a little bit. With that, I want to end all of this discussion with some open problems. Now we can relax, and let's just end this. I don't have a lot more to say, but just discuss some open problems in the field, and then we can go for some questions. Open problems, in my opinion, I mean, this is things that I just would like to point out. One thing, just one slide, right? I mean, I don't want to say much more, just I have mentioned this before, is just this issue about thermalization. So that's an open problem. We should always remember that we don't understand just yet from fundamental principles how this thing becomes a fluid. And it appears very clear that there's no thermalization itself, but it's also very clear that it's not a bad approximation to use hydrodynamics after some time. So to really reconcile these two kind of concepts is a challenge itself. And I hope that someday someone will explain what's really going on here. The other issue that's a little bit more resolved, not resolved, I guess people just accepted, right, is this issue about what is the smallest droplet of QCD matter that you can produce. So at the very beginning, yesterday, I said that it was very important to collide heavy ions because we need a large volume to produce a large system and try to get the thermodynamic limit somehow. But then people start doing proton-gold collisions, deuteron-gold collisions, and helium-gold collisions, things like this one. So these here are hydro simulations of a PA collision, how it evolves with time. This is deuteron-gold, this is helium-gold, and you just treat them as a fluid and you evolve with time. And more importantly, you describe the data. So this is deuteron-gold V2 as a function of PT. And this was even a prediction. This was a prediction by Peter Bozek. So, and it's head-on. I mean, it describes pretty much this flow observable with the hydrodynamic model in deuteron-gold collisions. And then later calculation by Romaczki for helium-gold and also deuterium-gold for V2 and V3. And it also very well described by hydrodynamic models. So a very quantitative description. So this was even published in Nature Physics. So it appears to be very, to have strong evidence that these systems are also like a droplet of QGP matter. And this just put my previous slide even more important, right? So how the hell is this happening for such small system, right? We don't really know. And this I mentioned yesterday, and I come back to this now. So hydro is working well for a small system, but if I look to the largest one, then we have a problem. So we have this kind of non-hydrodynamic behavior in these ultracentral collisions. And by ultracentral, it's very extreme. So the CMS collaboration, they can measure, for example, in this red point, collisions which are from 0 to 0.02% with the most multiplicity. So the most multiplicity collisions, they should be the largest system we produce. And if you follow the red point, this is essentially the Fourier coefficients Vn for V2, V3, V4, V5, V6. And if you go to the, let's say, central collision, which is this purple point, it behaves like we expect from hydro. It just falls down, right? And this in hydro, this is very, this is usually a feature because the dissipation kind of dampens these the smaller distance scales and makes these things kind of become smaller and smaller as we increase n. But as you go to ultracentral, it becomes flat here. So you see that even V2 is smaller than V3. This is very difficult to explain with any hydrodynamic model. And so far, it hasn't been. So no one can do it. And usually people avoid doing it. Of course, we are Brazilians, so we don't care about pissing people off. So what we did is we showed, again, this is a problem. So we made sure to make a paper just to point out that this is a problem, which is usually something you shouldn't do, right? You write papers with solutions, not with problems. But so in here, we just took this Bayesian analysis from Jetscape that fits everything, but does not consider ultracentral collisions. So it fits everything else. So essentially, all the parameters are fixed. We know the viscosities, and we know the most likely values for them. So we just took this optimized calculation that fits everything else with all the parameters fixed, and we calculated it for ultracentral. And we showed the following. So this is like our calculations here for several different global fits. So this is Jetscape, and this is the Dutch global fit called Trajectum. Up here is the data in gray. And again, you see that the ratio of V3 over V2 kind of is way larger from the data than what we get from any hydro model. But again, this is already optimized hydro model. Like all the parameters are fixed, so essentially you cannot fit the data. And the band here from our calculation is when we vary around the most likely value of each parameter in the model. So this band is kind of our uncertainty and is no way close to this ultracentral case. So to me, so essentially this shows that adjusting the model parameters will not really work. It's not like, oh, if we switch a little bit these optimized variables from the Bayesian fit, maybe we can fit this. No, you won't. You need something new here. So something new must be included. And if I knew, of course, I would tell you, but I have no idea. I have tried this many times. But it is ironic that hydro works for this very small system where it shouldn't work. By shouldn't mean we thought it didn't work. But then where it should work, there's just something missing here. It's suspicious. This I agree. What people think, of course, people are not stupid. I mean, people know of this. What people think is that there's something in the initial state that will fix this. There's just something missing, initial conditions that somehow we don't have in our models. But still, no one knows what this is, right? If it's initial condition, we don't know what feature is missing yet. Another open problem, which I don't really work on, but it's very important, is about just taking these hydro simulations and extending them to finite net baryon density, and also including the physics of a critical point. This is difficult from several perspectives, but also in the sense that, even having a hydrodynamical theory near a critical point is non-trivial, because the fluctuations become larger, and you have to address that. So you need to kind of understand how to include this physics in the models that we have so far, and in particular, how do fluids behave near a critical point, and have that for the fluid dynamical theories that we so far use. So
in this case, you'd have to use, because you said you consider net charge equals to 0 usually, and in this case, you'd have to consider it different from 0.
Yeah.
And from a certain critical value of it, you change your...
Yeah, so you need some equation of state, which has a critical point, for example, as a free parameter. If I put it here or there, like you should be able to vary it. That's hard enough. And you have to understand how your transfer coefficients would be affected by a critical point, and then also add that into your model. And then you have to see what are the effects on the data and see if you have or don't have a critical point. This would be the, let's say, naive way to explain it, or how they would show it in Global Reporter, right? The simple-minded explanation. A lot of people are trying to do this, but it's difficult. And so far as I know, they haven't found any evidence of a critical point. Like it doesn't seem to be, the data, at least just look at the data, nothing remarkable appears to be happening as you go to smaller energies, right?
But I mean, say it again, where the information that it is a crossover enters in your
in our current models?
Yeah.
So in our current models, it enters in the equation of state. So the pressure is just a smooth transition between a hadron gas and a deconfined phase. And in principle, it enters also in our choices of the transport coefficients, just continuous functions of temperature and so on. If you have a critical point or even a first order phase transition, maybe you have to be more careful on how you guess these coefficients. The other issue is that also, if you go towards finite densities, all your transport coefficients will depend on temperature plus everything else. And that's also, you have to kind of understand how to guess this dependence, or how having a critical point will affect the qualitative behavior of your thermodynamics and transport.
But can you use like two different equations of state, one for the crossover and the other one for second order, and then see where they match?
I don't know. I mean, without a critical point, it's easier. So let's say one thing that one can do is, okay, forget the critical point. Let's just put a first order phase transition here. And if we see a first order phase transition, we know there was a critical point anyway. Right? So we don't have to worry about details of if the fluid passes through here, let's just ignore the details of this critical point.
But you say you cannot do it.
I mean, you just have to guess all of this. You have to guess a pressure, which has a first order phase transition. And when you remove all the density, it matches the lattice one. So people are doing this. It's just not that easy.
No, you can compare it to B-managed scan data or...
Yeah, exactly. That's what they're doing. But again, they haven't found any obvious sign of a critical point. But they're looking very seriously. They're really trying to put all of the physics in the model and see if there's a systematic way to find an effect. Because maybe what people thought initially was that having a critical point here would be a huge effect. Right? I put this and suddenly I would see something somewhere. But that's not really what happens. And the reason is very simple. It's because we don't have a fluid in a box at the critical point. We have an expanding medium that will pass through this critical point very quickly. And what you have to understand is how much of the effect of a critical point will survive this. So it won't be that much, right? So in the end, you may be looking for a small signal, and that's why it's important to model this whole thing properly. Like at least I think, I'm not from this specific part of the field, but I think it's very clear that there's no clear sign of a critical point. That won't happen. It will be something hidden in somewhere, because the medium is just passing through this, right?
Yeah, I mean, what I don't understand is, because, I mean, your problem is basically optimizing parameters, let's say like that.
Yes.
And in this case, I mean, I see it in the same way, but with more parameters. That's what I see. I don't understand why it's much more complicated than that. I mean, it's enough complication anyway, but...
It's more because you have more parameters, and you don't know if the effect of a critical point could be compensated by some other parameters. So that's kind of the problem, right? Maybe if I just put a critical point, maybe I see, oh, this thing increases. But then you realize, oh, but this could also increase if I change the other 20 parameters in the model. So how do I distinguish a critical point from changing 20 parameters in my model? That's, I think, what's hard. On a lesser level, yeah. So right now, no, because some things are just undetermined. So so far, we put some shear viscosity and we kind of find some preferred shape. So it comes out. But you have a definite answer on the critical point. You need to have some data that will be sensitive to it. That's the problem. Like the fact that you're going to run a Bayesian analysis doesn't mean that you're going to get a definite answer for your question. Because maybe the data that we have doesn't really distinguish or see this critical point that well. I don't know if I'm making myself clear, but kind of, okay. Okay, later we can discuss. My last two slides, so also spin hydrodynamics. So this is the very interesting thing found at RIC, where essentially one thing that people realize is that the heavy ion collisions have one of the largest angular momentum in the world, right? I mean, it's a huge angular momentum. I guess for the same reason we have a huge magnetic field. We just have these huge currents separated by some small distance. And what people see is that essentially this angular momentum can be transferred to spin or polarization. So our kind of, this orbital angular momentum can be transferred to spin. So our rotating fluid essentially makes all the spin and polarization of the hadrons align with it. And this was measured by STAR. So they measure essentially the polarization of lambdas. And they saw that it was aligned with the angular momentum of of the heavy ion collision.
Just, I mean, Fernando Gardin said, I think it's also important to have a 3+1D hydro computation in order to search for a critical point and also a better equation of state.
True. I completely agree with them. So now people now also are searching for some hydrodynamical theory where the spin degree of freedom enters, and you can kind of calculate how angular momentum is transferred to spin throughout your evolution. This appears to be necessary to explain this data. And a lot of people are working on this, and I think this was the main result from heavy ion physics in the last few years. It made a big splash. And as my last slide, not last, okay, this one as well. I forgot about this one. Okay, maybe it's not that important, but it's more for myself. It's not an open problem, but it's a direction where I think we kind of have to go. So we study hot and dense QCD matter, and now it appears to be more likely that this has to be studied in astrophysics, right? We have a lot of signals from astrophysics due to gravitational waves and other telescopes, which appears to allow us to study, hot and dense QCD matter in astrophysics. In particular, in neutron star mergers, you can get temperatures and densities that are comparable to those that we have even in heavy ion collisions, in the most low-energy ones, but comparable to heavy ion collisions. So I think in the future, it's very likely that a lot of us will start migrating to astrophysics and starting simulating star mergers as well as heavy ion collisions. And I don't know, maybe this critical point will be found by these people, not by us. That's a possibility, that by doing star simulations and supernovas, not supernova, but neutron star mergers, they can see something about a critical point. And finally, that's the effect of magnetic fields. This is the interest of everyone who's in the Zoom meeting. And there's this big question about these fields are, of course, extremely large. We know this. There's no doubt about that. And there are these two questions that I would like to pose. And, first, whether these intense fields can affect the initial state physics. Maybe it's not as catchy as affecting the QGP, but at least at the initial state, we know they are large. So maybe they will change. Some of the things I said here today could be affected by putting these huge fields there. And no one has done it so far. So there's some room for this. And second, and I guess what also a lot of people believe, is whether these fields will live long enough to affect the QGP. That's another problem. It will depend on things that we don't know. And I guess to know this, we have to make a simulation and check. There's no other way. But still, these are interesting questions that I think one has to address. And I think magnetic fields are indeed a huge ingredient missing from these models, right? I mean, it's something that's very large and is completely ignored, even where it shouldn't be, like initial state physics. And one has to check whether something has to be done there. So I have no conclusions. So was that a question or? Yes.
Do you have an estimate about how large is the magnetic field compared to the pressure?
To the pressure?
The pressure of the fluid. I don't know if this...
Well, magnetic field is expected to be around 10 to 19 then.
Yeah. I even heard 10 to 20, so it's 10 to 19 then. The people keep pushing it up. I would
stick with
19, okay.
We don't know. I mean, this is the theoretical prediction, and then like the first experimental, if you can call like that, evidence corroborates.
My question lies because in one numerical method, SPH, there is a problem between the magnetic field and the pressure of the fluid. This could be problematic if the magnetic field is bigger than the pressure. So
but maybe you think about the kind of magnetic pressure term, and when you compare that to the pressure of the... I don't know if this will be... So when you compare this to pressure, you have, of course, to think, pressure, when, and like at what temperature and what. So it will depend, of course. But I don't know any of these numbers by heart. For me, the magnetic field is always 0. That's the problem, right? That's the problem. But I can check some numbers and see if I can answer your question later.
Thank you.
Either way, this is my last slide. As I said, I don't have any conclusions. My only hope is that these 2 seminars were of any useful at all to any of you. So if you learned something, I'm happy. If you haven't learned anything, you don't have to tell me that. You can just keep it to yourself. But if you learned something, you can tell me later that you learned a lot and so on. With that, I thank you all very much.
Okay.
I'm open for questions.
Let's thank Gabriel. More questions?
Nope.
Someone say, thank you very much, great talk. The motivation to use a conformal pre-hydro model is because at early times we are probing very high temperatures and the bulk viscosity should be negligible.
Mm-hmm.
So just to say that anyone who wants to ask a question in the online audience, you can just open your microphone and ask, or you can send me a written question and I will read it.
But this was a comment from someone, right? That's what you... question or?
A question. The motivation to use a conformal pre-hydro model is because at early times we're probing very high temperatures and the bulk viscosity should be negligible.
Yes and no. I mean, so what he or she is saying is that is a justification for the approximation. So at very early times, this is the justification, but it's of course half right, half wrong. I mean, so of course at very early stages, what we have in a heavy ion collision is not one temperature, but a temperature distribution. So indeed, there's a huge part of the fluid which is at a very high temperature, and there it's approximately conformal, but it's a temperature profile. It will go to 0 at the edges. It has to. There's no way around it. So there will be always, even at the initial condition, there will be some region where the conformal approximation is not very good. And that's where these kind of conformal models will fail. Is it a big failure? Some people believe it's not. I mean, others. So this is something that we have actually estimated using our models, and we do see some effects of breaking this kind of conformal symmetry, but it's not a dramatic effect. It's not something that will render everything wrong. But I understand the comment. I mean, indeed, a lot of people think that if at the early stages, it's good enough to think it's conformal, to make that approximation, even though it will fail at the edges of the fluid where temperature has to go to 0. Okay.
More questions?
On spin hydrodynamics, we will not use Boltzmann equations for the...
Or if you can do it with Boltzmann equation, or... So the people who are doing this, they are doing it from a kinetic point of view, but they have to extend the Boltzmann equation with a leading quantum correction. So it's not the usual Boltzmann equation, it's what they call a non-local Boltzmann equation. That would be, let's say, one way to describe this if you believe you have quasi-particles. The other fundamental ingredient is that essentially you have some uncertainty principle. So now the particles don't collide exactly at one single point. There's some fuzziness where they can collide, they can interact at essentially different points due to the uncertainty principle. And once you make the collisions non-local, they have angular momentum. And this angular momentum can be exchanged with spin. And you start this kind of description like that, right? So from a kinetic point of view, that's where you come from. But in kinetic theory, you can only do a quantum correction. So you think that, okay, it's not classical, but I just correct a little bit, the leading H-bar correction. Now, these equations are very complicated, extremely complicated, and I think people are still a little bit far from applying them to heavy ions. I think the Polish have a simplified version of that, where more like a toy model description of this. But so far, all that I know is from kinetic theory. But in principle, it should exist a more general framework. Okay.
Thank you.
Okay, I have one more question. How is holography helping to understand the hydrodynamic behavior of these systems?
That was a few years ago, maybe 10 years ago, the leading explanation. So for some reason, these things are kind of cyclical. So they come and go. So back in the day, people thought using kinetic theory to describe this thermalization process is just hopeless. And you need some kind of strongly interacting description like holography to explain this very quickly thermalization. But I don't think there has been a lot of new results on that on the last few years. The last person working on this, I think, is Larry Yaffe. They tried to describe in holography heavy ion collision as two kind of like shock waves colliding in this kind of dual space. Like they try to mimic a heavy ion collision in this dual space in holography, and then see how that system thermalizes or not. In their approach, it always thermalizes very quickly. So that's for sure one ingredient. But one has to ask like how to do a realistic model of that. I think that's where holography kind of fails. They never can integrate their description into our models in a general way. So there was a meeting in Santa Barbara like last year where they combined a lot of people and discussed this. And one of the things that we asked the holography people are like, can you give us a pre-thermalization package that we can actually run in our models and check if yours is better than theirs? And they were very interested in doing this, but at the same time, the reality is very complicated to do in practice. So they're trying to. So you need some kind of bubble gum package, right? That plug and play, that can be used easily, and the transport people did that. So I showed you the equations they solve, and they just simplify to a level where it's very fast and quick, and we can just use it. And so that's the advantage. But holography is an explanation, and some people think holography is a natural explanation for this very quick hydrodynamization that we have. Yes. Yes. Then you have to explain holography. So, yeah.
Yeah, and basically they show that if they do things in a dual space, they reproduce the data, but things in the dual space is not what is going on in this
They
space.
don't,
So it's
they don't even reproduce the data. I mean, sometimes they don't even go that far. They just show that, okay, this is what we think a heavy ion collision looks like, in our formalism, and then they show kind of what happens. And okay, does it thermalize? Does it not? What's going on here? That's what they show. Like to compare to data, then, because the real holographic models, they are conformal, all the way conformal. And so sometimes they take QCD and they make a holographic model which they can match to QCD somehow. Those are conjectures, I guess. They just assume that, let's say this is valid, I could just break conformal symmetry with some scale, and then I match it to get the right pressure. And then you go all the way. The only person that was doing that I remember was Jorge Noronha, and he's not giving that much time to this anymore. So, I shouldn't say this, but I mean, the problem is sometimes with holography, people get very excited, and they do all the simple calculations that exist, but then no one wants to do the complicated model building to describe the data. Like that's sometimes something people don't think is very attractive. But of course, for this is required. You must, if you want to really make statements, you must do a proper model, fit the data, and see what you can find, right? You cannot just.
I could say the same about us.
True. It's always part of the evolution that you first start to solve all the easy problems, and sometimes not the easy ones, but let's say without a heavy ion collision. But sometimes it's not easy to find a smoking gun observable that will just give you what you want, right? You really need to work out the whole simulation and see how your effect entangles with all the other effects that we have, and to check if it can be possibly disentangled from all of this. Like, as I said, I think initial state physics may be a good avenue for this. I mean, there's a lot to do there, and maybe some effects can be found there, right? And they could also be the easiest thing to do right now as well. But that's just a guess.
Okay. So just to conclude, so getting back to magnetic fields, if it's to affect initial state, I mean, so for you, what is useful for you? I mean, if I tell you how magnetic fields affect inequation of states, I guess, so, or how it's generating an isotropy, what is the quantity that for you it would be useful, especially in the initial state?
Oh, initial state essentially, we look. Yeah, this
F0,
F0.
that's it, right? And F0, I mean, it enters F0 through this anisotropy parameter. That would be,
for example,
right?
But also, I mean, if I go back all the way, maybe this is not obvious from what I said, but from the data, we usually can measure very well this initial shape here. So how elliptical it is, how triangular it is, like all the eccentricities, we can pretty much see this effect all the way to the observable when we measure those VNs. So also if the magnetic field changes the thermalization process in such a way that the shape is modified in any way, this we can see almost immediately. And since there's some preferred direction, maybe it will happen like that. Maybe it does change it. I mean, so that's one thing. That F0 as well, if the initial pattern distribution is modified, that for sure will or could make a difference. You mentioned something I never thought before.
So when you say the shape, you mean pressure? I
not
mean,
pressure.
different
Literally is
literally the shape.
the shape of this thing. Yeah, how it's distributed and how elliptical it is, for example. If maybe a magnetic field made it more elliptical, and it's not a small effect, then we can see it. We can see this.
Okay. I mean, in the case of the ferromagnetic effect, they elaborated all these isobar collisions because they couldn't disentangle effects from magnetic field and effects from the
From flow.
geometry that comes natural from the collisions. See, I don't know if in other kind of effect it would be.
Maybe the initial velocity distribution of the medium as well could be affected. Things like that. I mean, anything on the initial state, which is a visible difference, in principle matters. Right?
So it would be F0, velocities.
Yeah. The energy distribution in the sense of the shape itself, like how, if the system is more eccentric, more elliptical, that's important. We can see that.
Yeah, I mean, if it lasts time enough, then it would affect the crossover. I mean, it would still be a crossover because you'd need a much larger field to make it first order, but you can change the...
So now you're talking about the medium,
let us
right?
call it critical temperature.
Yeah.
I mean, it's not critical temperature because it's not a real phase transition, but, you know, like the
So now you're assuming the magnetic field survives long enough to affect the medium, and then you change the pressure,
then it
stuff
would
like
change the critical temperature. This is
I
something
think,
else.
I mean, maybe I'm saying something wrong, but I would imagine that, let's just assume that the magnetic field is 10 to 20 Gauss throughout the whole collision. Let's just say this is true.
No way, but okay.
No, it's not true, but let's say it's true. Then for sure there will be an effect, right? I mean, because then the pressure will change significantly, and there's no way we don't see this, right? So suddenly, if the magnetic field is large enough, we see something. The issue now is whether it survives long enough to affect the medium. So that's the most difficult thing to know. And since this will depend on some kind of conduction of the medium, the only way to know this is to actually do a simulation with the medium and a magnetic field and actually run the simulation like a plasma physics really and see and calculate this field, right? But that's, we're still very far from that, I think.
I mean, but it would enter in many different places. I mean, if it lasted a lot, then it would affect not only, magnetohydro, but I mean, a lot of things would be different, right?
I mean, if it lasted all the way to particularization, it affects particularization.
Yeah.
Right? When you produce the particles, the F depends on B as well, if B is large. So in principle, if it's large, it affects all the stages. And then the question is it large, right? The only place we know for sure it's large is this very beginning.
Yes.
So that's what I think is
Fernando is
place.
asking for how long B survives. We don't know. So I mean, because we don't know if the medium is being magnetized. So there are some simulations that say that it's not magnetized, but these are very simple simulations. So it could be still.
But let's say
there's still room for
without
it
a
to
medium,
be. But
how long
anyway,
does it decay?
then it's a few Fermi.
A few Fermi.
Yeah.
That's even longer than, it's a few Fermi to go down from what to what? Do you remember the numbers? Like it's 10 to 19 gauss. How long does it take to go?
How many orders it?
Yeah,
No, I have to check. But then, I mean, what I can say is that the effects we see, we need it to be very strong.
Okay.
Otherwise, it's not relevant. Then, I mean, after a few Fermi, it's still, it's not that.
Yeah.
But then it's not enough
it's
to
pretty much zero. Okay.
yeah, to see what we see, like affecting phase transitions or affecting mass spectra or things like that, or particle production.
Okay. Okay. One thing I never thought about was whether the magnetic field affects the wave function of the nucleus. This could be also. I don't
Yeah.
know. Yeah.
I mean, this would be one very.
With magnetic field? Okay. It changes significantly. So Gaston's saying that with the Valleca model, they have checked if the wave function changes with magnetic field, and it does change a little bit or somewhat, I guess. Yeah. This no one has considered, and maybe it's important.
So Fernando is asking, is this computing using NGL? Which computing, the how long B survives? Is that your question? No. No, people used Maxwell equations. And then the
I think it's the field produced by the spectators, right? The
yes.
spectators, these moving charges, right? They are sources of a field.
Yes.
And it's huge because the current is huge. And then, but of course, they fly away very quickly, so the field goes down. That would be the naive story, right? And then the question is how the medium can induce more or less. Or so
yeah, and then there are simulations, numerical simulations to check if the medium responds to this field. But no, but then, I mean, NGL, yes, it's used to see, I mean, if the field is there, then people use NGL to check how it will be affected. Like, for example, I said it changes critical temperature. This is calculated using NGL. And other models, right? But not the intensity of field with time. Then no.
I actually have a question to anyone. I mean, in the audience. I mean, do you guys have tools to solve the Maxwell equation in 2 dimensions or 3 dimensions? Let's see if one can do the hydro with magnetic field. Can anyone do the Maxwell equations? With the sources, the currents from the medium, or that's too far yet from?
No, I mean, in this group, I think nobody has done that, but other people have done that. Like Tushin, Tushin has done that.
Has done it. Okay. Yeah, this is.
Student that works with magnetic. So
yeah, she's trying to solve hydrodynamics. So he said, I have a student doing this magnetohydro stuff. I do, but so far she hasn't worried about how to solve the Maxwell equations, like in a general scenario,
numerical perspective.
Numerically, like in 2 dimensions and so on.
Was what I know about in SPH, we don't have any, but we have some grid methods. I don't know
to solve it. Yes. So someone would have to do that, and maybe. So I don't know how difficult this is. I mean, if someone has a good Maxwell solver, we can just do a trivial hydrodynamic model, just putting conductivity and check. I mean, like just putting conductivity on the hydro model is not that hard. If you just do that, ignore all the rest, and then couple to Maxwell's equation, and then you can really do a more precise simulation. That is not that far off. But the difficult thing,
what people did, I mean, in the simplest way possible.
Yeah, I think they did Bjorken, no? It was just Bjorken, but I wanted a full 2D and so on, 2+1D simulation. We just do ideal hydro with some electric current or whatever, and see what happens. I don't know if that's feasible, but that's one idea.
On the Jetscape observables that you showed, polarization is not included.
No. So Jetscape so far does not have any spin physics, any of it. So they cannot describe. So for them, the lambdas come out with like random polarization, it doesn't, it's not aligned with anything. So this is not included, yeah.
You can get the magnetic field from the linear weighted potential T.
Okay, so
Yeah.
you don't. But you still have to integrate with some general source, I guess, or.
Hmm?
Because see, now we have this kind of, the source would be the medium, which you have to solve dynamically. But I get it. Okay, so you can just, like the potential solution of the Maxwell. I was more worried about you have the Maxwell equation and then you have sources. Now these sources should be from the medium itself, which we solve
Yes.
like with fluctuations, all that.
Yeah.
So the Maxwell equation should also be able to handle that type of.
It does sound complicated.
Yeah, I never tried to solve them, so in this sense, so I don't know.
Okay. More questions?
Nope.
No, if not, let us thank Gabriel again.
Thank you. So now.
Thank you all for coming. I will close the room now, and I will upload it soon to our YouTube channel, and it will be also uploaded to ICTP Cypher channel. See you.